Okay, so today we are talking about tangent lines. Like we've learned before, tangent lines are just lines that intersect a circle at exactly one point. We have two different types of tangents. We have a tangent line and then also a tangent segment. That tangent segment is part of the tangent, right? That's our point of tangency, and then a point outside of our circle. So it's just a portion of this line cut off, right? Again, tangent line hits that circle at exactly one point. When we create our radius and we draw it to our point of tangency, this is something new, right, that we're applying for today. We create this perpendicular relationship. So from our center of the circle to the tangent point, yes, that's our radius. The important thing about this is that we're creating that right angle. We have that perpendicular relationship. So again, we should be thinking about our right triangles here. Let's do a couple examples involving this idea about creating our radius to our point of tangency. We're given this circle G and T as a point of tangency. If GE is 20, so we have this whole length of 20. We have our tangent ET as 18. We're asked to find the radius. Yes, I see we have that portion, right? This portion of that EG is a radius. Not so helpful though. Let's create that radius to a point of tangency, thus forming our right triangle. From here, let's label that value as r, x, whatever it happens to be, and then set up our Pythagorean theorem. We have our leg squared plus leg squared equals hypotenuse squared. We solve and simplify this. Subtract that 324. And then think about what's a perfect square factor that divides into that 76. Rewrite that radical as root 4 by root 19. Square root of 4 is 2. Square root of 19 is square root of 19. So our radius of the circle is 2 root 19. Excellent. Same idea for our next one in example 2. We're given this circle F. R is that point of tangency. We want to find the diameter of the circle. If we're given DI is 8 and then RI is 12. So let's label those segments that we have, right? We have this DI, which is that external portion of our secant. That is DI 8. RI, that tangent line, or tangent segment, is 12. We're asked to find the diameter, which really, right, we can find that diameter if we determine that radius. So let's draw in our radius of FR and label that as R or X. When we create this Pythagorean theorem, right, we need the whole side of our triangle. FI is that whole side. We need to create an expression to represent that. FD, we can label as R because that is a radii as well, meaning that whole hypotenuse would be R plus 8. Let's set up that Pythagorean theorem. We have our leg squared plus leg squared equals hypotenuse squared. We simplify this. On that right-hand side, we have to take that R plus 8 squared and rewrite it twice. R plus 8 by R plus 8. So we do have some algebraic steps to go through in order to solve. Let's share, right, that R to both of our second parentheses, right, thinking about foiling. Same thing with that 8. and then continue to solve. Something I'm noticing about this expression right off the bat, we have an r squared on both sides. So if we were to subtract an r squared, those things cancel. Thus, when we're continuing to solve, we don't have a quadratic anymore. We just have this linear equation. It makes it a little bit easier. Divide both sides by our 16, and we get r is equal to 5, making that diameter 10. All right. There are some tangents are next. Let's draw two tangent segments from our circle A to T. We're going to call those points of tangency X and Y. So we're creating two tangent segments. Our tangent segment on the top, oops, you guys can probably draw it a little bit better than I can. There we go. Tangent, right, XT. And then we have this bottom tangent that's a little curved, bottom tangent of YT. Something we can conclude about these tangent segments is that they're congruent. They are equal to each other. Why we're able to make that conclusion, we're going to go back all the way to our congruent triangles unit in semester 1. If we create our radii, right, we know that our radii are congruent. So AT or AX is congruent to AY. Cool. If we draw in this segment of AT, that is a segment that's in common between both triangles. That's the reflexive segment. So we have two pieces, right, in both of those triangles, in that top triangle and that bottom triangle. Something that we can also put in deals with our radii drawn to our points of tangency, that theorem that we just learned today. So at that point of tangency at Y and also X, we can put those right angles. So we know that each of these triangles are congruent by HL. So therefore, we can get those last two remaining segs congruent by CPCTC. Crazy, right? I know that was a really very large throwback. But again, the main point of this is to conclude that those tangent segments are congruent. So let's look at a couple examples to demonstrate this. We have this circle W. A and M are our points of tangency. We have AR, that length. We have MR. Again, we know from above that tangent segments are congruent. So we have our 5x squared is equal to 2x squared plus 27. Then we solve. Subtract that 2x squared on both sides. Divide both sides by 3 to isolate our x squared, and then take the square root. We get two solutions, x being equal to positive 3 and also negative 3. We do want to test to make sure both of those solutions work. So when we plug this in, we get 5 by that 3 squared, which would be 49 or 45. Same thing in this bottom, 2 by 3 squared plus 27, 45. When we plug in that negative value, when we take, right, that negative 3 and square it, negative 3 by negative 3 is 9. So both of those solutions for x work, and we can conclude that that MR has that single length of 45. All right, I'm going to have you guys try one, right? Go ahead and pause the video. I want you guys to try number 5 and try number 6. So here are our two solutions. For number 5, we'll get AN to be 16. For number 6, we'll get AY to be 30. For number 5, I encourage you to solve for that whole length of your hypotenuse of GN. Yes, we know AG is 10, but I do think it is a little bit, I guess, more efficient to solve for that entire hypotenuse length rather than create that expression of 10 plus x and square that value. It works this way just because when we have that whole length, we could subtract our little portion of it. For number 6, you can use those ideas that we had from yesterday. So when we create that distance to our chord, we have that right angle, that perpendicular relationship, and we have at that point our diameter, which will split into 2. And then we have that 8, 15, 17 right triangle. So that little portion of our chord is 15. Our other chord is 15, making that whole chord of 30. So this one was more of a review recap from yesterday. Okay, the last thing that we need to chat about today is this idea about our circle that is inside of our triangle, or maybe it's a rectangle, right? This triangle is circumscribed around this circle, in this case it's circle R. We're asked to find the perimeter of that triangle. So something to think about here, right, is we have a bunch of tangent segments. If we just focus in on this MK and this KN, right, that is a tangent segment, and those two lengths are congruent. So I know MK and KN both are 7. Same idea as we work around the outside of this figure, right? Tangent segments show congruence. JM and JO, right, are going to be the same. And then OL and NL, those are tangent, and those two segs are the congruent. So let's set them equal to each other and solve. And again, the reason we're able to do this is because of those tangent segments. We get x is equal to 4, and then we can plug that back in to find our length of NL and find that length of OL. Again, if you've done that correctly, you should get the same lengths for each of those tangents. Now to find the perimeter, right, all the greens, the reds, and the blues added together, we just add up all of those sides. So to find that perimeter, we're taking our green segs, our blue segs, and our red segs, adding them together, and we'll get our 52 units. All right, why don't we try a little bit of a review of our tangent segs and tangent secant angles. I will pause the video, stop the video, and upload this key on Canvas for you to check out the solutions for this. Remember, big recap is to think about where the vertex, right, of each of these angles are. So for 8, right, we have our 2 points of tangency, tangent angles, vertex is outside of the circle. For 9, we have a tangent secant, vertex is outside of that circle. So go ahead and give these a shot, and then check those answers on that note key on Canvas.